This lecture is going to talk about the algebra of functions. So we're kind of looking at, again, this chapter is kind of dealing with more on functions. So we're going to talk today about, what happens when I add functions together, subtract functions, multiply and divide. It's going to do exactly what you think it would do. The thing that can be a little bit tricky with this is just finding the domain. So let's just start with the definition like we usually do. And the important part of this definition really is at the very beginning. Okay, so definition, let's let x be in the domain of f of x and in the domain of g of x. So when we're talking about adding two functions, subtracting two functions, multiplying or dividing two functions, I have to make sure that both functions can handle any x value I give it. So if I have a number that's in the domain of f but not in the domain of g, then when I start combining these functions together, that's not going to work. Both functions have to invite those x's to the party, okay? So let's write down kind of what I think once I do examples, it'll probably be a little easier to see that. But just notation-wise, one way we can do this is we can say f plus g of x. What does that mean? What am I going to do to the two functions? Exactly what you think you would do with the two functions. You're going to add them, right? It says add, so we're going to add them. Same thing with subtraction. What is f minus g of x? What is that function? How do I get that function? I just subtract them. And I know this notation seems kind of like, well, yeah, Sarah, that's obvious. And it is, and it should be. But I think I really want to drive home that if I have two functions, when I add them, the result is a function. So you see I'm using this function notation. Same thing when I subtract two functions. As long as they're both functions, the result will be a function as well. And that's kind of the cool part about it. Fg of x is exactly what you would think. I'm going to find that new function by multiplying the two functions. And then this one, of course, is division. That's my last one. How would I get a new function from two functions? By dividing. Well, I just divide the two functions, provided that. Now, here's where we have to be a little bit careful. Is we have to make sure that we are not grabbing x's that would make g 0. Because, just because x makes my function g 0 doesn't mean it's not in the domain of g, right? That's a valid number that's in the domain of my function g. But if there are any x's that now make g 0, we have to throw those out because, of course, we're dividing and we know we can't divide by 0. Okay, all right, cool. Let's do some examples. So a couple quick examples that'll be kind of easy here. Let's let f of x equal 3x squared plus 1. And let's say g of x, let's just kind of keep this simple, equals 4x minus 2x squared. Okay. So let's evaluate a couple things here. Let's find f plus g of x, and let's determine its domain, just for fun. I know what you think is fun, and fun is adding functions, doing an algebra of functions. So this is pretty simple, you guys. I'm just going to take f, which is 3x squared, right? I'm going to add it to g, which is 4x minus 2x squared. I'm going to combine like terms. I'll kind of, hopefully you agree with me here. And there's my new function. So notice, that makes sense, it's a function, right? It's a quadratic. So I have my new function. Part B, what if I asked you to find f minus g, let's say, of 1? Well, one way you can do this, there are a couple ways you can do this. You could find f minus g of x, right, and figure out what that function is and simplify it. Or we could actually just find, if we go back and look at our definition, it's just my function minus my other function. So that's going to be true for numbers as well. So this is, it's getting very angry at me. Okay, oh my goodness. So I get f of 1. I could also do this, f of 1 minus g of 1. And if I look up here, f of 1 is 3 plus 1, which is 4. Up here, g of 1 is 4 minus 2, which is 2. So what is f minus g of 1? That is 2. Okay, I hope that makes sense. And then let's look at something like this. F divided by g of x and its domain. I'm going to write it down here so I can work to the right of it here. Okay, so that's where these are pretty straightforward, I think, until maybe we get some domain going in here. So let's see what f divided by g of x is. So remember, if I'm talking about domain, oh, I didn't do domain up here, did I? Oh, man, that's horrible. Let's see what the domain is up here. Sorry about that. Remember, the domain, I have to include x values that are included in the domain of g and are in the domain of f, okay? So what is the domain of 3x squared plus 1? That domain is minus infinity to infinity. And what is the domain of g of x? This obviously is minus infinity to infinity. So what's going to be the domain when I add these two functions? Same thing, guys. Everyone is invited to the party, right? F invites everyone, g invites everyone. So my domain is going to be minus infinity to infinity. Whereas when I have division, even though g invites everyone to the party, the problem is now there could be some x values, and there are, that make g 0. So while, yes, f and g, their domain is everything, we have to consider now that g is in the denominator and it is dividing. So I have to look at, okay, where is this guy 0, right? And we talked about this before. Where do we have issues? Well, I might have a lot of issues, but we have issues where we have zeros in the denominator and negatives under the square root. So if I look at this, what can x not be? X cannot be 0. Sorry, this is getting kind of squished. Or 2. So what is the domain of this function then? I did not plan this out very well, but you're probably used to that by now. The domain is everything but 0 and 2, so I could go minus infinity to 0. Whoa. 0 to 2, union 2 to infinity, or in set notation I can say it's all x except, oh, hold on, we're not all x's. 0 and 2 are not invited. Okay, so that's kind of what we mean when we're combining functions, or we're taking the algebra of functions. So let's look at another example, maybe with some fractions, because I know fractions can kind of be confusing sometimes. So how about, let's see, just trying to think of one that would be kind of interesting. Let's consider f of x equals 4 over x plus 1, and g of x, let's say, is 1 over 6 minus x. Okay, so let's look at what would happen if we started combining some of these. So, you know, if let's say I wanted to find f minus g of x and its domain. So before I really get going on these, what I like to do is I like to say, okay, so what are the domains of my functions as is? If I look at f, where am I going to have issues? I know that x cannot equal -1, right? Or else I would have a 0 in the denominator. And if I look at g, I know that x cannot be 6. So I'm just going to keep that in the back of my mind and realize that if I have any combination of these two functions, I'm going to have to be very careful to make sure that -1 and 6 are never invited to the party. They can't be invited to the party because f doesn't like -1 and g doesn't like 6, so we can't have a party where those guys are coming in. Even if g likes -1, right? F and g are throwing a party together, so even if g likes -1, f doesn't, because so we don't want them at the party. We don't want to have some issues, okay? All right, so f minus g of x, I'm just simply going to take 4 over x plus 1 minus 1 over 6 minus x. I'm going to simplify this a little bit by getting a common denominator, of course. Whoops, sorry, my battery's running now. Let me plug that sucker in really quick. All right, So I'm going to get a common denominator. Oh, that probably made it a little brighter, so that's kind of nice. Should have done that before. I'm going to multiply this one by 6 minus x over 6 minus x. Multiply this one by x plus 1 over x plus 1. Good old common denominators. We love them, don't we? So what do we get here? I'm going to get 4 times 6 minus x minus 1 times x plus 1 all over, and I'm just going to leave that denominator as is. I'm not going to FOIL that out. And so what's my final answer here? Well, I would have 24 minus 4x minus 1 minus 1, right? So it looks like I have a negative 5x plus 23 all over x plus 1 times 6 minus x. And then again, what is my domain here? I'm lazy, so I'm going to do set notation. It's all x such that x is not equal to negative 1 and 6. And you can kind of see that because what are the two factors that would make me have a 0 in the denominator? It would be negative 1 and 6, right? Let's try g divided by f of x. Okay, so g divided by f of x and its domain. Let me be a little bit better about that. And its domain. Okay. So g divided by f, I'm just going to do exactly that. And I have to remember, if I'm doing division here, I got to make sure if f can be 0 at all, I need to throw out any x's that can make f 0. However, if you look at f, I have 4 over x plus 1. I have a constant in the numerator. That means it can never be 0 because the only way for a fraction to be 0 is if the numerator is 0. So I actually don't need to worry about that, which that's kind of nice. So I'm going to write this nice and big. I'm going to keep this nice and neat. I'm not going to try and do this in my head, especially when I have fractions over fractions. So let's see what we get here. So I'm not going to leave it like this either. That's gross. Remember what we do when we divide by fractions. I don't really memorize little tricks. I think one of my students was telling me about like keep, change, flip or something like that. You just got to remember, and whatever works for you, if you have a little saying, do it. I just always mess up my sayings. But how do we divide by fractions? We multiply by the reciprocal of the denominator, okay? So the reciprocal of the denominator is x plus 1 over 4, and now it becomes multiplication. So look at what my final answer would be. We have x plus 1 over 24 minus 4x. And what is the domain of this going to be? Now, that domain, you guys, is still going to be all x such that x is not negative 1 or 6. It's pretty clear to see that x can't be 6, but some of you might be like, but Sarah, that x plus 1 moves up top. You guys, x plus 1 was never invited to the party in the first place. X plus 1 was never invited to the party because, or excuse me, negative 1 was never invited to the party because x plus 1 started in the denominator, and f of x isn't even going to send an invitation to x plus 1, okay? Sorry, negative 1. Negative 1. So no matter what happens later on in the night, even if x plus 1 turns out, or negative 1 turns out to be a stand-up guy or gal, it doesn't matter because they didn't get an invitation. So even though, again, that x plus 1 came to the numerator and my original function here, f is never ever going to invite negative 1. It's not even on the table. So it's not in the domain of any kind of combination with f and g. All right, I want to do one more of these and then we'll talk about simplifying the difference quotient. So let's look at another one. I want to do one, this one could be quite interesting. Let's look at f of x equals the square root of x plus 6 and g of x equals 1 over x, okay? Again, before I get going too far, what I like to do is I like to find the domain of each function. So what do I have to worry about here with the square root? We need to stay positive. We always want to stay positive when we're dealing with square roots, right? So look at the domain of f. The domain of f then is going to be everything bigger than negative 6, right? So negative 6 to infinity, and then g here is everything but 0. So again, I'm just jotting these down because then I know any combination of these two, I gotta make sure that I'm satisfying both of these domains. So let's start off kind of easy. Let's say I wanted to do g minus f of x, okay? Now, there's not a whole lot you can do here, people. I'm just going to leave it like this because I can't really simplify that anymore. You could get a common denominator if you wanted to. Okay, so I lied there a little bit. If you wanted to get a common denominator, you could do this, but I don't think you need to. I don't see how it really helps us. So either one, I would take either solution. Now, let's talk about the domain. Remember, I have to satisfy both of these. So if I'm at -6 here, so f is going to grab everything here, right? However, there is one value in there that we have to be careful about, and that is x not being 0. So look at this. So even though f is fine with x being 0, who is not okay with x being 0? That would be g. So we have to take that 0 out. So when I'm talking about my domain, what I need to consider are these two intervals. I need to consider this interval right here, which is -6 to 0, not include 0, and then union, right, this interval here, which is going to be 0 to infinity. I hope that makes sense. I got to take that 0 out because, again, 0 is not invited to the party. All right, let's look at another one of these. So what about if I did, let's do g over f of x, and then we'll do f over g. So g is 1 over x all over f, which is the square root of x plus 6, right? Now remember, this is all over 1. So what do I do with fractions when I divide by them? I flip them and multiply. So look at what I have now. I have 1 over x times root x plus 6. So we already know that I'm going to kind of, my basis for my domain here is going to be this guy. Because this guy right here, this is taking care of all of the x values that g can't have and all of the x values that f can't have. But then I have to think about this a little bit, because remember, I'm dividing by f here. So I need to figure out, are there any x values that would make f 0 that are now included in the domain and shouldn't be? Well, there are. Look at, if I square both sides, I get x plus 6 equals 0. So when x is -6, do you see how that would make the denominator 0? And you can just see that by looking at the new function here. So I have to take -6 out of my domain. So my domain is going to be very, very similar, except instead of having a closed or square bracket around -6, I have to have an open. Okay, so there we go. There's my domain. Hope that makes sense. These are kind of fun. They're easy because you're just like adding and subtracting, but sometimes that domain can be a little bit tricky. So if you have questions, please ask them. All right, guys, and then the last thing that I want to talk about that is in this section is something called the difference quotient. And the difference quotient, the unfortunate thing here is that we're going to talk about the difference quotient, and you're going to work with the difference quotient, but then you're not really going to see the beauty that the difference quotient is until you get to calculus. Why do we do it in algebra though? Because this is all algebra. So really what the difference quotient is it's a mixture of adding and subtracting functions, and it is a way for you to just practice your algebra skills. And once you get to calculus, once you have this skill, it'll be easier when you get to calculus to find that derivative. So what the difference quotient gives us is it gives us the slope of a secant line between 2 points on a function. So for example, let's say I have some point right here and a point right here, and I want to find the slope of this line right here. Well, what I'm going to say is I'm going to say this point right here, and this is without loss of generality, right? Throw this into the first quadrant. Could be in the second quadrant, third quadrant, doesn't matter. But I'm going to say I'm going to take some point at some x value, and then I know this is a little strange, but what I want is I want to take another point that is just a little bit away from x. And so what I'm going to call that little bit away from x, I'm going to call x plus a little bit more. So that means this at this distance right here is h. And honestly, we could go to the left of x as well. We could take h could be negative. If h was negative, I would take x just a little bit to the left. But if you notice, that's that difference right there. And if I look at the points that I have, so this point right here, what would the coordinates be? It'd be x, comma, what would my y coordinate be? It'd be my function evaluated at x. And then right here, what would the coordinates of this point be? It'd be x plus h, and then f of x plus h, okay? And then what the difference quotient gives me, okay, so this is what the difference quotient gives me, is it gives me slope of the secant line. Another way to think of it is it gives me an average rate of change, because it's basically the slope of the line between these 2 points. So it gives me the average rate of change of that function. So the difference quotient is basically finding this slope. So let's find this slope. So remember, slope, right, is the change in y's. So I'm going to do the change in y's. I'm going to take the f of x plus h first minus f of x. So there's my change in y. Now all over change in x. So I have x plus h, right, minus x. And if you see, this simplifies pretty nicely. So here's what my difference quotient is. My difference quotient, or the slope of that secant line, or another way to put it is the average rate of change of my function, is f of x plus h minus f of x all over h. Okay, and again, this just allows us to find maybe the average change. If I went from like 1 to 1.5, then I know that h is 0.5, and it's an easy way for me, if I can simplify this whole expression, it would be an easy way for me to see the change, or the average change, quickly if I had a lot of points maybe I was trying to go through. So I'm just going to show you a bunch of 2 examples of this, maybe 3, we'll see. And again, the idea of this, when you get to calculus, what you end up doing is you let that h go to 0. It's really cool, really, really cool. You let that h go to 0, and what that does is it forces this point to come and match up with this point, and you get the slope of the tangent line, which is so great. Okay. All right, so let's look at a kind of an easy example. Find the difference quotient. Being kind of lazy. For the function f of x equals 3 minus x squared. Okay, so here's the difference quotient. It's f of x plus h. I'll give that to you. There's no need to memorize that, but I do want you to know how to simplify this. Okay, so look at what f of x plus h is. This first part right here, f of x plus h. F of x plus h means take your function and evaluate it at x plus h. So what does that mean, to evaluate a function at something? It means anywhere I see an x, I am going to replace it with whatever's in the parentheses. This is a hard concept. If I asked you to find f of 1, right, what would you do? You would take 3 minus 1 squared. So same idea here. Whatever's inside the parentheses is what I'm going to replace x with. So this f of x plus h, I'm going to take 3 minus x plus h, quantity squared. Then I need to subtract just the function itself, making sure to put parentheses if I have a minus, or if I'm subtracting more than one term, right? You must put parentheses if you're subtracting more than one term. I'm going to simplify this. Don't make mistakes. Don't take that negative through first. You must FOIL the x plus h's together first. I can take that negative through though, that's okay. And people, if you do this correctly, your h and the denominator should cancel out, because then when you get to calculus, you're going to let h go to 0. I'm just going to square this for you. I'll let you verify when you FOIL that sucker that this is what you get. So go ahead and you can do that. I'll pause the video and FOIL it out really quick. All right, I'm showing every single step. Take the negative through. Notice how I put this all in parentheses because I'm subtracting the whole thing. So I'm going to take that negative through. All right, so here's the fun part. So you do all of that. And now notice I have a lot of things that are going to cancel. My 3's are gone and my x squareds are gone. And what do you notice about what's left? Do you see that I have an h in everything that's left? That's really good. If you do the difference quotient correctly, you should have everything left should have an h. Okay, everything left should have an h, so that that denominator h will cancel out. So there's my final answer, negative 2x minus h. That is the difference quotient. So if I wanted to know like the average rate of change of this function as x changes from 1 to 1.5, I would put in 1 for x, I'd put in 5 for h, and there's my average rate of change. I don't have to go through the whole process of like finding the actual difference in the function, dividing by a half. That's what's kind of cool about that. And then you'll see in calculus what happens as that h goes to 0. It's so much fun. All right, let me do one more quick one. Maybe two more? We'll see if we have time here. Let's consider f of x equals, let's just do 1 over x. Okay, f of x plus h. So when you are dealing with fractions and the difference quotient, the trick with the fractions and the difference quotient is going to be to get a common denominator. So what does it mean again to take f of x plus h? It means everywhere I see an x in the function, I'm going to replace that x with x plus h. Okay, now I'm subtracting just the function itself, which is 1 over x. I need to get a common denominator here because, again, I want this h to cancel. Don't you dare cancel those h's right there. Don't be crazy. Don't be canceling those h's. I need to get these together. Let's get together. Yeah. Get these together, these fractions together, so that I can pray to the math gods that the numerators will have just an h in it and I can cancel. So let's look at what we're going to get here. I'm going to get x over, right, x times x plus h. I usually don't FOIL that out. Minus x plus h over x times x plus h. Now you could. It's not wrong to FOIL that out. You sure could. And this is all over h. So let's simplify this a little bit more. That means in the numerator, I'm going to get x minus. Now this negative needs to go to each term, right? Because I'm subtracting that whole numerator. All over x times x plus h. All over h. Now I'm going to remember this is h over 1, so I'm going to use the trick of what do we do with fractions, right? When we divide by them, we flip and multiply. But look at what I can get here. Those guys are gone. So what is the numerator left with? Negative h over x times x plus h. And then that fraction right there is going to multiply by the reciprocal of this fraction. Isn't this cool? And those guys are gone. I love doing these. That probably doesn't surprise you. I just think they're so much fun. Look at that. That's it. That's just a good time, you guys. That's just a good time. I don't know. I don't care who you are. That's just a really, really good time. All right, let's do one more and then we'll call it good. So with a fraction, when you're doing difference quotient with a fraction, what you need to do is get a common denominator. Let's look at what would happen if I have a square root. So let's say I have the square root of 1 minus x. So we'll do this one and then we'll call it good. F of x plus h, then minus f of x all over h. Again, what am I going to do? I'm going to do a little bit of side work here, but f of x plus h, that'd be the square root of 1 minus parentheses x plus h. I'm subtracting more than one term. So I'm going to go ahead and write that as 1 minus x minus h. Take that negative through, minus the square root of, oops, I'm getting ahead of myself because I know what's going to happen here. 1 minus x all over h. Okay, again, my goal, right, is to simplify this so that my h would cancel. Well, what we're going to do here is we're going to do a lovely little trick that we call multiplying by the conjugate, or another way to think of that is I want to rationalize the numerator, okay? So, you know, you learn how to rationalize denominators. While maybe rationalizing, square roots in the denominator maybe aren't that big of a deal as much as they may have been when we didn't have calculators, rationalizing is an important concept to know. So while it's not always like needed when we're dealing with just numbers, rationalizing denominator, being able to rationalize a numerator or a denominator is important because it comes up in stuff like this. All right, why did I multiply by the conjugate? Now, I did it to top and bottom, right? So this is the trick you're going to use when you have square roots. You're going to multiply by the conjugate, and here's why you're going to do that. Look at what happens when I multiply these two right here, when I do FOIL first. Then they're the same thing under the square root, so they're just going to cancel out. Now, what I want you to notice is when I do outside, I'm going to get this guy times this guy, and it's positive. But then, guys, when I do inside, I'm going to get this guy times this guy, which is exactly the same as the product before, except it's negative. So what happens is it's a difference of squares. Those middle terms cancel out. If you don't believe me, that's okay. If you don't believe me, FOIL that out and see that the middle terms cancel. And then I'm going to do last. What do I get for last? I get a negative, right? Of those two multiplied together, they're the same thing. So this is just 1 minus x all over. Look at how nice this is. Oh, I always forget my denominator here. Did we finished that last problem, right? My h is canceled now. I don't know what I'm doing, you guys. Does that worry you a little bit? So I get 1 minus x minus h. Yeah, we did. Minus 1 plus x, take that negative through, all over h times root 1 minus x minus h plus root 1 minus x, okay? So this is the fun part again. I know you're like, but Sarah, that was all fun. I agree. And now look at what we can do here. Even my h's can cancel. So what's my final answer? Negative 1 all over square root of 1 minus x minus h. Again, I know we're not doing a lot with the difference quotient right now, but it is really pure algebra, and that's why we're doing it in an algebra class. And I can't wait for you to get to calculus and see how beautiful this is in calculus. All right, let me know if you have any questions.